Okay, hello everybody. So today we're going to be starting a new chapter on functional groups. So this chapter kind of acts like an overview for the rest of the textbook. So from pretty much this point on, we're going to be honing in on specific functional groups. Now, the next chapter is a little bit different because it reviews acid-base properties, which are relevant to all functional groups. But from that point on, there's going to be a focus on a particular chemistry set of molecules that do a particular type of chemical reaction or have certain type of chemical and physical properties. So collectively, those things are known as functional groups. And so we're going to be talking about some common ones that you're going to encounter in this class. So let's start off with a little bit more succinct definition than the kind of rambling one I just gave you. So what a functional group is a special group of atoms that gives molecules specific chemical and physical properties. Kind of like what makes them stand out from other molecules. So one thing we're going to be addressing here is a concept that you talked quite a bit about in general chemistry, and that is solubility. So the rule of thumb for a solubility is like dissolves like. And if you remember those intermolecular forces we talked about, it has a lot to do with those. So in other words, polar solutes dissolve in polar solvents. Polar solutes dissolve in polar solvents. And also non-polar solutes dissolve in non-polar solvents, which we kind of went over a few of those last time. So let's look at a molecule that has several different kinds of functional groups. So I'm going to start off by drawing a six-membered ring. So this is a benzene. And it's going to have coming off of one side of oxygen, and then a carbon double bonded to oxygen. We refer to that as a carbonyl. And then on the other side, we have a carbon that's going to be double bonded to an oxygen, and then that's going to be single bonded to an oxygen and hydrogen. Okay, now the first thing I'm going to mention here is that you'll see oftentimes we condense certain functional groups into a specific shorthand. So another way that I could have written this molecule is instead of drawing out all of the this carbon double bonded to the oxygen with the OH, I could have also written it out the CO2H. We're going to go over the specifics of that later. But what I want you to see here is to notice that there's a hydrogen here, and that is bonded to an oxygen. So there is definitely some hydrogen bonding that can occur in this molecule. And so the name of this compound, this is known as acetyl salicylic acid. Okay, but we know it as aspirin. Okay. Now, you may look at this and go, okay, it's polar, it should dissolve in water at the end. Well, that's only part of the story. See, the thing is that even though it has polar bonds, meaning it has bonds like, the carbon bonded to the oxygen and the oxygen bonded to hydrogen, it has even more non-polar bonds. Okay, if you look at this, there's a far more carbon to carbon and carbon to hydrogen bonds in this molecule than there are carbon to oxygen or oxygen to hydrogen bonds. And so those kind of weigh out, okay, in terms of what the molecule generally prefers to be dissolved in. So based on its structure, do you believe that aspirin is soluble in water? Okay. And the answer is, well, only a little bit. Only a little bit soluble. It's not very soluble in water because it's mostly nonpolar. So what I'm trying to get at here is that be careful with blanket statements about polar and nonpolar. Technically, a molecule can be polar, but it may have very small, okay, polar properties associated with it. So always consider the big picture when you're looking at the compound. Right now, the first, I guess, kind of family of molecules that we're going to be talking about, and this will be the first ones that we address. I believe we'll get to them in chapter 4, is a family of compounds known as hydrocarbons. And hydrocarbons are just that. They contain only carbon and hydrogen in their structure. All right, and there are two big categories of hydrocarbons. Category A is what I'm going to refer to as aliphatic. So aliphatic hydrocarbons. You can think of those as non-benzene. Non-benzene hydrocarbons. Okay, for right now. And then for B, there's another family known as aromatic hydrocarbons, and you can think of those right now as benzene hydrocarbons. Now, that's kind of a, that's not a complete definition, and the word aromatic is a very broad and important term that's talked about in second semester. But for right now, just kind of equate that benzene is different from your typical aliphatic molecules. It has its own set of properties, and that's what you need to really be thinking about here. So for instance, if we look at this compound, so this is C6H12, so there's 6 carbons and 12 hydrogens here. The name of this molecule is cyclohexane. Hex is 6 carbons, and it's a cyclic structure. And this is something that is aliphatic, okay? Versus, say, if you were to have benzene, which is like this, and it has the chemical formula C6H6, okay, and technically it has, an IUPAC name. It's like a 1,3,5 cyclohexatriene, but everybody refers to it as benzene. And you will often see it abbreviated as a PH, okay, which is short for what is known as a phenyl ring, okay, a phenyl ring. And again, this is referring to compounds that we think of as aromatic, which have a little bit different properties, okay, than aliphatic compounds, but both are hydrocarbons. Now, in this class, the major focus on hydrocarbons is definitely going to be in the aliphatic camp. And so that's what I want to start talking about right now. So the focus in 2341, Organic 1, is on aliphatic hydrocarbons. Okay, so number 1, the first family of aliphatic hydrocarbons is something that's known as an alkane. Okay, alkanes are made up of only carbon-to-carbon single bonds. No pi bonds, no double bonds, no triple bonds. And we refer to systems like this as saturated, okay? Meaning the molecule has as many hydrogens on it as possible, okay? So double bonds or triple bonds or pi bonds are what we lead to what are known as unsaturation, okay? So some examples of some alkanes is one we just saw a moment ago. So that was cyclohexane. Again, notice the ending ane, A-N-E. also, let's say if you had a 4-carbon system, C4H10, this is a butane. Okay, we're going to get into nomenclature in chapter 4, but I'm just kind of pointing out those endings now to you that that's not a mistake. Now, for alkenes, which is the second major type of aliphatic hydrocarbon, an alkene contains at least one carbon-carbon double bond, okay, or one pi bond in its system. And we refer to systems like this as unsaturated, meaning, okay, technically you could make more sigma bonds there to hydrogens if that wasn't double bonded. So some examples of some alkene structures. Let's look at a 5-member ring here. So if I were to put a double bond here, this would be cyclopentene. Notice that it doesn't matter where you put the double bond here, that would be equivalent at all positions. So I could have also have drawn it like this, and that would essentially be the same molecule. You just need to rotate it. And this is going to be a big thing in this class, is recognizing when you're looking at the same thing or two different compounds. Now, butene, on the other hand, okay, is a little more complicated. So, for instance, if I put the double bond right here, okay, this is a butene. But is that butene the same thing as this butene? Okay, and is that butene the same thing as this butene? All right, because all of them are a butene, meaning it has 4 carbons and a bond. Well, the first thing to point out here is, again, that stuff about the numbering. Okay, if I were to number this, I could say, well, the double bond here starts at number 1, okay, and we could call this a 1-butene. But sometimes it's not that simple. So, for instance, down here, I could do this and go, okay, always go with the lower number. So I could say this is a 2-butene. But the problem is, well, so is this one. And are those even the same compound? And the answer is they're not, because in order for this carbon to be pointing in the same face as this one, you would have to rotate. And there's no way you can rotate around a pi bond because you would break the pi bond. So with these types of systems, you have to go a little bit further. So notice the direction here that the groups that, you know, kind of one group is pointing in this direction and one group is pointing in the other direction, like they're in opposite directions. We refer to that as a trans. So this is trans 2-butene. And if the two groups are pointing in the same direction, well, then we refer to that as a cis 2-butene. Okay. Now, all of these compounds are related to each other, and that they all have the same chemical formula, meaning all of them have 4 carbons and all of them have 1 pi bond, and it means they have the same number of hydrogens. So there's 1, 2, 3, 4, 5, 6, 7, 8. So all of these have the chemical formula of C4H8. Okay, and so that means that they are all isomers. Okay, so isomers are different from resonance structures because they are different molecules, meaning I would have to actually break a chemical bond in order to make them interchange. Okay, so let me just reiterate that again. So what is the difference between a resonance structure and an isomer? Well, the answer is that a resonance structure, you are talking about the same molecule. Okay, in other words, all the different ways that you're drawing it all represent the same molecule. You're just looking at different pictures of it. Resonance structures are like if you have a camera and you're trying to take a picture of the three-dimensional object. Now, sometimes that's very easy if the object is small, but imagine if you're up close and you're trying to get a picture of, an animal that's large, like a horse. Well, you could take pictures all over the horse, its tail, its head, its hooves, everything. But one picture would not define the animal. You would need all of them to kind of get a good model. And that's how resonance structures are. They all represent the same thing. Whereas an isomers are just flat out different molecules, period. Okay, they are not related. They're not the same thing. Okay, so we're comparing something like a horse to, say, something like a donkey. Okay, so those are not the same animal. Okay, so that's one of the critical things to kind of be thinking about. And there are a lot of questions in the homework that deal with those types of concepts. Now, there's one more hydrocarbon, aliphatic hydrocarbon, that I want to mention here, and that is what are known as alkynes. Okay, so that's ALKYNES. Alkynes contain at least one triple bond, one carbon-to-carbon triple bond in their structure. And they are also considered to be unsaturated as well. Now, with these systems, I've mentioned this before, if you have, let's say, a 5-carbon pentyne, and you want to represent that, so let's say you had this kind of structure here, just draw it out in a condensed formula first so you can see that, okay, in fact, it has 1, 2, 3, 4, 5 carbons in it. If you wanted to draw that in a skeletal structure, it is tempting to always start the structures the same way, like this. But I would recommend that you don't do that and that you pay attention to the geometry here, and that it's actually 120 degrees because that carbon is sp hybridized at 2. So really the best way to represent this molecule is like this. Okay, now you could have drawn, you didn't have to go down like that. You could have continued the structure up. That would have been fine as well. Okay, those are appropriate. And if you go off at an angle, make for sure you continue out, okay, going in that same direction. So 1, 2, 3, 4, and 5, okay, until you have all of your atoms. So this is compound known, obviously, this is 1 pentyne. Now, if I wanted it to move that triple bond into the system, like if I wanted to represent, let's say, 2 pentyne, well, then I would need to start off with a single bond, 1 and 2, then a triple bond, where 3 is going to be, and then 4, and then 5, like so, okay? And 2 pentyne and 1 pentyne are most certainly isomers. Those are not the same molecule, okay, because of the position of where the triple bond is. Now, just before we get into, getting into a lot more details about functional groups, there is some common shorthand that you should be aware of. Some common shorthand that we use to represent functional groups to emphasize a specific functional group. To emphasize a specific functional group, we often abbreviate large portions of the molecule using the letter R. Okay. Now, for the letter R, the R is short for a type of species that's known as a radical. And what that essentially means is that it carries a single electron. Now, since every atom has at least one electron in it, well, then that really means that R could represent anything you want it to be, okay, including hydrogen, all right? So oftentimes it's necessary to specify what R is not, rather than saying what R is. For instance, if you had, let's say, this molecule, okay, and you were not interested in the fact that it had this many carbons in it. You just wanted to show that it was a transalkene and that was it. Well, then what you could do is you could say, okay, I'm going to say that I have an R here, and then I have a double bond, and then I have another R here. And to indicate that those two R's are different, you will see this little prime that's used here next to it to indicate that those are not the same thing. This is what's called R prime. And if you had three, then you would have two of those little click marks there, and that would be R double prime, etc. Now, what I would want to say here is that R and R prime are not equal to hydrogen in this case, okay? So that is clearly telling me that this is a transalkene, okay, without having to write the whole molecule out. Now, trust me, they get a lot more elaborate than this, but that's just kind of telling you, I guess, the gist of how it works. All right, now we're going to start talking about some things that you guys are going to want to, you're going to want to memorize for the upcoming exam. So this is by no means a comprehensive list, but these are the ones you should definitely get under your belt, okay, by exam one, because they are very common. So this is what I'm going to refer to as non-hydrocarbon functional groups. Okay, and you should memorize these by exam one. Okay, I'm going to break this into two families of functional groups. One family is going to be referred to as non-carbonyl. Okay, what I mean by carbonyl is that there is no carbon double bond oxygen in any of these that I'm getting ready to talk about. Okay, so the first one is if you have an R group and it's bonded to an oxygen and a hydrogen. Okay, so this is referred to as an alcohol. Okay, if you have an R group, again, the R groups can be hydrogens, okay, but if you have three R groups, or just, or some of them could be hydrogen, what's important is that there's a lone pair on the nitrogen directly. This is referred to as an amine. If you have an R group and it's bonded to another R group, and in this case the R groups are not equal to hydrogen, well then this is referred to as an ether. Okay, E-T-H-E-R, ether. All right, if you have an R group that's bonded to a carbon that's triple bonded to a nitrogen, this is referred to as a nitrile. Okay, if you have an R group that's bonded to a halogen, so we use X in organic chemistry to represent halogens, so that means X, it can be equal to fluorine, chlorine, bromine, iodine, etc. Any of the halogen families, so the family that's like right here, excuse me, focus, there we go, right here, right before the noble gases, so this family of elements here, those are what are known as alkyl halides. If you have a sulfur in place of an oxygen, those are known as thiols, or just a thiol, Thiol. And if you have an R group that's bonded to a nitrogen, that is double bonded to an oxygen and single bonded to an oxygen, drawing the formal charges, it also can be written out as RNO2. Well, then these are known as nitroalkanes. Okay. Now, the second big group of molecules that you're going to see in here are the carbonyl containing. Okay. And again, these are going to be ones where you have a carbon double bond oxygen and it is directly associated with the atoms that are around it. So the placement of the carbonyl is very important. So for instance, if you have a carbonyl, okay, and that it is directly bonded to a hydrogen after that, this is referred to as an aldehyde. Okay, and an aldehyde has a common abbreviation of CHO. Okay, so that's very confusing. Sometimes people will associate that with an alcohol. It is not. Okay, it is shorthand for aldehyde. All right, another one is if you have a 2 R groups here, and again, the R groups are not equal to a hydrogen, that is referred to as a ketone, K-E-T-O-E. Oh, excuse me. And if you have a carbonyl and it's bonded to an oxygen and a hydrogen, this is referred to as a carboxylic acid. And I've already mentioned its abbreviation, which is CO2H. Then if you have one where you have an oxygen, but it's bonded to another R group, and again, here R is not equal to hydrogen in this case, these are referred to as esters, ester, E-S-T-E-R. And if you have carbonyl bonded to a nitrogen that has a lone electron pair, and again, the R groups here don't have to be carbons, they can be hydrogens as well. This is referred to as an amide or an amide. And carbonyl bonded to an X group, these are referred to as an acyl halides. Okay, so like I said, it's not, that's a lot of different functional groups, but that's not a comprehensive list by any means. But if you have thumbed through your textbook a little bit, you should have, you will recognize some of those names as they are names of many of the chapters that we're going to see going forward in this class. Okay, so now a couple of other things to mention here before we wrap things up. So one of the things that is very common with functional groups is their level of substitution. So many, and I often refer to functional groups as FGs, so many functional groups can have more than one R group attached to them. And so it is important to note this feature as it relates to the compound's reactivity. In other words, it's chemistry. And we often refer to this in organic chemistry as how substituted. We often ask, how substituted is a group? Question mark. Okay, so we're going to start off with alcohols. So if you have an alcohol, look at the carbon that is bonded to the alcohol, okay? And look at how many hydrogens are bonded on that carbon. Okay. Notice that there is only one non-hydrogen atom here. Okay. There's only one non-hydrogen atom here. Okay. What we would say 1R group. Okay, group that's not a hydrogen atom. Okay. This is what's referred to as a primary alcohol. And we often abbreviate that with a 1 and a degree symbol for primary alcohol. Now, if you look at this alcohol here, all right, and you look at the carbon atom that it's bonded to, notice here there's now only one hydrogen. Now there are two R groups. Okay, well, so we refer to this as a secondary alcohol, or 2 with a degree symbol. And if you look at an alcohol where you have no hydrogens attached at all, okay, and you have 3 R groups associated with that. Then this is referred to as tertiary alcohol, or 3 with a degree symbol. So this primary, secondary, tertiary is used in several different functional groups to talk about a molecule's substitution. The tertiary is more substituted than the secondary, is more than the primary, and that affects their chemistry. Okay. Now, if you were to look at, say, an amine, well, amines are really even easier than alcohols because all you have to do is look at what's attached to the nitrogen. In this case, there's only one R group attached to the nitrogen, and so this would be referred to as a primary amine. And if there were 2 R groups that were attached to the nitrogen, well, then this would be referred to 2 R groups. This would be referred to as a secondary amine. And if there were 3 R groups attached to the nitrogen, again, here the R's are not equal to hydrogen, 3 R groups, this would be referred to as a tertiary. Okay. And we can also relate this to alkyl halides as well, which are very similar to alcohols, meaning if this is an alkyl halide here, there's 2 hydrogens. This would be a primary alkyl halide. If there was only 1 hydrogen on that carbon atom, this would be a secondary alkyl halide. And if there were no hydrogen atoms on the carbon atom attached to the halogen, then it would be a tertiary alkyl halide. Okay? And the primary, secondary, and tertiary also apply to carbons that are deficient in octets, like carbocation, which we mentioned in chapter 1. So for instance, this carbon atom here lacks a 4th group, and so it has a positive formal charge. This is referred to as a primary carbocation. If it has 2 R groups associated with it, then this would be a secondary carbocation. And if it had 3 R groups associated with it, would be a tertiary carbocation. Now, I don't know if I mentioned it or not, but I want to mention it now, which is in all 3 of these cases, all 3 of these carbons here, what is their hybridization? And if you said sp2, well, then you are correct. Okay, there's only 3 groups around those carbons, and so by definition, they are triple planar and sp2 hybridized. Okay, that will be a very important down the road. Okay, so the last thing I want to do is kind of go through an example question with you guys. So this is going to be the last problem that we're going to work in today's lecture. So let's have a look at this. So identify the non-hydrocarbon functional groups in here. And if you see any functional groups like, alcohols or amines, indicate if they're primary, secondary, or tertiary. Okay, so go ahead and pause the video, and then we're going to go through and talk about what it is. Okay, so the first thing that stands out to you, okay, is, well, what's up with this direction here? Like, why is there this wedge? And so this is indicating that alcohol group is coming out of the page. And so this is very common in organic chemistry, and it's important, even though it's not drawn in, that implies that there is a fourth group, okay, where there is a hydrogen pointing back. So that tells you that that is an alcohol that has a carbon that's bonded to one hydrogen. And we define those alcohols as secondary alcohol. Okay. Now, this is very easy to look at and go, oh, there's a tertiary amine, the end. But the problem is that the carbonyl is present as well. And so that counts as part of that functional group. So the nitrogen goes with the carbonyl, so technically this is an amide on amide. Okay. And then over here on the side, you have another carbonyl functional group that's bonded to a hydrogen, and so those are known as aldehydes. Okay, now I know that that was a lot of information, and you probably had to go back and look at your notes to do that. But that's the kind of question that's very common that you'll see here in the beginning about identifying functional groups in the molecule. A lot of it is, do you know it or do you not know it? And so that's why I said you really do need to know those, because it will be beneficial to you in the long run. Okay. Now, the next lecture we're going to be doing, I'm going to be going over PowerPoint on IR spectroscopy. And so I'm going to pull that up next time. That's going to be available to you on Canvas. And so you can pull it up and look at it there as we go through it together. Okay, guys, so if you have any questions or concerns, just feel free to email me or put a comment section, and I'll get back to you as soon as I can. Hope everybody's doing okay. Take care, and I'll talk to you again soon. Bye-bye.